you going? Is anybody else, when you're in here, experiencing any kind of allergies or anything? Or is it just me? Nothing?
I got pretty bad last week.
What?
Last week I was.
I mentioned this to my morning class. I don't know, okay, somebody mentioned about mold.
And the Haley, yeah.
No, I said, I was talking about here, but I don't know if that's true. Maybe it's just something else. But I've taught in this building a long time. But this is a weird feeling in this room. All right. So, we went to chapter 6. We just got done with, we did the reflections at normal incidents, the reflected and transmitted fields. Anybody have any questions about those? I'm going to do something right now. I'm going to continue with that, but I want to talk about shields. And the reason I'm doing it here and not later is because it makes a lot of sense to talk about shields right now after we do the transmission and reflection at of a normal incident wave. So this is further on to chapter 10, chapter 9. Shields, it makes perfect logical sense. Now, first, I want to just make sure everybody's got this down. When we're talking about any type of normal incident wave, by the way, I don't know what it is with markers, even after COVID, they seem, the ones that are in the main office, all seem to be questionable at best. So when we talk about two regions, and right now we're going to assume we have a region 1 that has a characteristic impedance of beta 1, and a region 2 that has a characteristic impedance of beta 2. In general, when we talk about characteristic impedance, it's equal to the square root of j omega mu over sigma plus j omega epsilon. And those are generally real, it can be a magnitude at an angle or real and imaginary part in general. Now, typically this is air in region 1, but it doesn't have to be. When you have this, and we're going to assume propagation occurs in the z direction, but the electric field will be oriented in the x direction. I'm going to do this for everybody's sake, so when I do the next step, you'll be reminded of what you have to know. So if we have an incident field right here, we can label it as some E naught incident, e to the n. Technically, let me say region 1 is lossless to be consistent with the book. So that means sigma 0. This is going to be E, and I'll call it air for now. So air also. It would be e to the minus j beta 1 times z a x. And that would be the incident electric field that's propagating this way. There's also going to be a reflected electric field. And I'm going to say that E reflected here is given by E naught reflected times e to the plus j beta 1 z ax. Does everybody understand the plus j is necessary because it's moving in the opposite direction? Okay? When we're taking a look at this, it gives rise to a forward propagating wave here in this region, and I'll call that E transmitted, and that's some E naught transmitted times e to the minus gamma 2 times z in the ax direction. Now I'm going to leave that as gamma because you know that gamma in general is equal to the square root of j omega mu times sigma plus j omega epsilon. So this region would be the parameters in region 2, and that's equal to alpha plus j beta. And I'm just showing you the electric fields. Everybody with me? There are also magnetic fields that you can get using the standard tricks that I showed before. I'll put them here in case somebody is interested. So if we want the H field and we have the E field, it's going to be 1 over eta, unit vector and direction of propagation crossed into the E field. And if we have the H field and we want the E field, it's going to be minus eta times unit vector and direction of propagation crossed into the H field. And those are just general for propagating waves, but only for propagating waves. Now we come over here, the H field incident will be equal to, and I can put it as E naught incident over eta 1, and this is going to be e to the minus j beta in region 1, but it would be in the AY direction, and this would be times z. Does everybody understand that? Now we proved that, right? We can get it from the right-hand rule. E crossed H is direction of propagation. The H field has to be in the Y direction, correct? It's propagating in the Z. And what is H reflected going to be? Well, it's going to be minus E naught, right? Reflected, pardon me. E naught reflected, right? Over eta 1. Remember the minus sign. E cross H has to be direction of propagation. If E is vertical and it's reflected, then H has to be into the board, which is minus Y. Correct, class? And this is going to be e to the minus, or plus, pardon me, j beta 1 z in the AY direction. And finally, H transmitted is equal to E naught incident, E naught transmitted over eta 2. And here it's going to be unit vector and direction of propagation crossed in. Let me do it this way. I'll put the whole thing down for you. So this is actually going to be E naught transmitted over eta 2, the e to the minus gamma in region 2 times z, and here it's going to be in the AY direction. I'll leave it like that. Now, eta right there has got a magnitude and an angle. Is everybody with me on this? Do you all remember basically getting these using those equations, but I'm leaving this as gamma 2. Okay, now we talk about the reflection and transmission coefficients, and you will get quizzed on this Friday, all right, because last time we didn't, but you'll definitely have to know. So when we take a look at the reflection coefficient, that's the ratio of E naught reflected to E naught incident. How many remember that? You're going to need to know this. What is the secret? Like that I always say. It's always the impedance you're going into minus the impedance you came from. So it'd be eta 2 minus eta 1 over eta 2 plus eta 1. It's very similar to the idea for the reflection coefficient on transmission lines. It's always the characteristic impedance of the load minus the characteristic impedance of the transmission line over the sum of the two. That's the reflection coefficient. This is for normal incident. And the transmission coefficient can either be given as 1 plus the reflection coefficient, or simply 2 times eta 2 over eta 2 plus eta 1. And I think we all know that, right? Okay, now, if you take a look at this, we could do a problem where I can give you certain values. We might want to do that just to confirm everything, because you weren't really quizzed on this, and a lot of times if I don't quiz you on something, you will not be prepared. In other words, you don't do a proper amount of studying of the material. How many looked at this, by the way? All right, this should be something, and you're going to need to know this very well because it appears throughout the course. So I want to do something simple. And All right, let's look at 638 for a second. And I want to do this problem, but the reason I'm going to do it, and that he's going to give a time domain form, the reason I'm doing this is to make absolutely certain that you guys understand all aspects of this kind of a problem. And so for this one, problem 638. Go ahead.
Suppose medium one is z less than 0,
Air,
it's
yeah.
air, and medium two is z greater than 0 as epsilon r equals 16.
What's mu r? Non-magnetic?
Yeah, it appears to be.
Does he say it?
There's no mu r.
What? Could read the problem. It's
No. The transmitted magnetic field intensity is known to be H transmit equals 12 cosine of omega t minus beta
cosine of omega t. Go ahead.
minus beta subscript 2 z in the AY direction. This is milliamps.
Milliamps. Milliamps per meter. Go ahead.
Yes. Part A. Determine the instantaneous value of the incident electric field.
All right. So he wants E incident. Now, does everybody understand? He doesn't say it's non-magnetic in there.
You didn't say so. But he doesn't have a epsilon relative.
Does he have an omega?
No, no. Omega.
Does he have any information about frequency?
No frequency, no omega. No beta.
This is not. Maybe this isn't the best. That's okay. We'll do it this way. We'll assume U relative is equal to 1. And usually he states it's non-magnetic. But if he doesn't, he doesn't, okay? Anyway, when we're looking at this one, let's put this in the phasor domain right away, okay? So we can take a look at H transmitted in the phasor domain. It has a magnitude of 12 milliamps, right? And it would be what? Just e to the minus j beta 2 z in the AY direction. And the unit, and it would be in milliamps per meter. Do you all agree with that? That would be the phasor form, right? We don't know what beta 2 is. If they don't give us does it give us beta 1?
It doesn't even tell you there is a beta 1.
Well, there has to be. If there's a beta 2, there's a beta 1. All right, so now we take a look at that, right? And we know, now here's the next thing we're going to do over here. For that problem, we need eta in region 1, which is going to be just, what, eta naught, or 125 ohms. Do you all agree with that, class? Right? And what is eta in region 2? It's lossless, right? So if it's lossless and we come over here, we know sigma 0, the j omegas cancel, we get square root of mu over epsilon, or square root of mu naught over epsilon naught. Right? Square root of mu naught over epsilon naught. And then it's just times square root of 1 over epsilon relative. You all agree with that? Do you all follow me what I'm doing? So the first part, square root of mu naught over epsilon naught is eta naught, or 125. Correct, class? All right. So that's just eta naught. And the square root of 16 is going to be 4. So it's really 125 over 4, right? Or it's 35, and I'm going to leave it like this, and the units will be ohms. Do you all agree with that? Okay. So now we'll go ahead and get, we're going to get the transmission coefficient. So the transmission coefficient is going to be 2 eta 2 over eta 1 plus eta 2, or it's what? 2 times, and this is going to be eta naught over 4 over eta naught plus eta naught over 4. I want you to just make sure you see this, because I know some of you haven't really spent a lot of time on this. You all agree with that? In the back, Andrew, can you read it? Okay, you with me? All right, well, what's that gonna be? You'll notice, well, we could do a lot of stuff, but the eta naughts cancel, don't they? Can you all see that? That's the reason I put it in terms of eta. Eta naughts cancel, so I get 1/2, right? And it's divided by what? 5/4? And what is that gonna be? So it's gonna be 2/5. Is that right, class? Or 0.4, correct, class? Read it, everyone? I'll take a moment. So that's tau. And now what is tau? Well, it's actually the ratio of what? E naught reflect, or E naught transmitted, right? E naught transmitted over E naught incident. We need E naught transmitted. We have H naught transmitted, right? How do you get E naught transmitted? Now, by the way, it's lossless, right? Can everybody follow me? Region 2 is lossless because there's no sigma. If that's lossless over here, then I know what? The ratio of E in region 2 to H in region 2 would be equal to eta in region 2. I hope you follow me. Do you agree with that, everyone? Okay, you all follow me? I'm making sure. So what do we know? We know eta 2, right? Eta 2 is going to be 30 pi. We know H2, 12 milliamps, so we can get the E field in region 2 that would be the transmitted field. The really E0 transmitted would be equal to eta 2 times H naught 2. And here, eta 2 is going to be 30 pi, right? And H is 12, but it would be times 10 to the minus 3. And this would be in volts per meter. So what is that going to be? Let's see.
2.825.
Thank you. 2.825, and that would be volts per meter transmitted.
So
So
that's it's 0.36 pi. That's the transmitted, right?
I want to know the value for the
I
transmitter.
got 0.36
Pi.
That was the incident.
5, did you say, or pi?
pi.
Okay, just leave it at 0.36 pi, and that would be volts per meter. Just leave it. Y'all agree with that? Now to get the incident field, we come over here, right? To get the incident field, we're going to take E naught transmitted divided by tau, or you can say that the incident field would be equal to E naught transmitted divided by tau, or it would be 0.36 pi, and it's divided by 2/5, or 2 times 5, and what is that, 0.18 times pi times 5. Anybody?
Is what you said is the 2.83.
Is that right? 2.83 volts per meter. Y'all follow me on this? We're just going through one problem to make sure, please. What's the next part?
Part B is find the reflected time average power density.
Reflected time average power. Okay. So that's the incident field. I'm going to go over here and use this portion of the board. All right, that's the incident field. I got, what's the reflection coefficient, class? You know, reflection coefficient plus 1 is transmission, right?
Yeah.
So if I take transmission coefficient minus 1, I get reflection. Do you agree?
Yes.
So that's going to be tau is 2/5 minus 1, which is 5/5, is minus 3/5. Do you all agree with that? That means the actual value of the reflected field, this is going to be just the magnitude, it's going to be the actual value of the coefficient, which is going to be a real number. So this, for this case, And that's the incident field is equal to reflection coefficient. So the reflected field itself is reflection coefficient times the incident field. Reflection coefficient is minus 3/2, or 3/5 times the incident field, which is 2.83. And what's that come down to? As far as, this is gonna be a negative value, that's okay. Anybody?
Negative 1.7. Let's reflect, yeah.
Volts per meter. Anybody confirm that? Okay. You all follow me with the steps taken? Now, that electric field is going in the it's propagating the opposite direction, but the power density to all of these, since there is no loss here, right? I mean, they're both lossless media, region 1 and region 2. The actual average power is real, in magnitude, it's going to be 1/2 magnitude of the E field squared divided by eta in the regions. Now that's the general form, and it will be in the AZ direction, could be plus or minus, depending. This one's propagating in the opposite or negative Z direction. Do you all agree with this, class? If we just worry about the magnitude of the power density that is reflected, that will be 1/2 magnitude of the electric field that's reflected squared over eta in region 1. So that's going to be 1.7 squared over 2 times 120 pi, and that would be watts per meter squared. Now we know, I'm implying it's propagating in the negative Z direction, so I don't put a negative sign. Are you all with me, class? I could put AZ here and put a minus sign here if I really wanted to be a stickler, but I understand it's going in the opposite direction. What is 1.7 squared over 240 pi? That's what he asked for, right? Power density reflected.
Power density, yeah, the reflected time average power density.
This is what do you,
1.7 squared over what,
240 pi.
240. We're in, okay. 3.8 milliwatts squared.
Meters squared. AZ, you can put, is that right? Y'all follow me on how to do, what else does he ask? That's a good one.
That's it.
That's it?
Yeah.
I did that for a reason. I want to make sure at least you have an idea of how to go about getting things. If the H field is transmitted, given, not the incident field, people need to be able to work these problems any which way. If you're given, you might say output before input, or transmitted field, H field before incident E field. You should be able to get that just going through your logical reasoning, okay? Yeah.
So were we finding just E naught incident in part A, or were we supposed to find the entire?
He asked for what? Just the electric field magnitude?
Instantaneous values and stuff.
Oh, if he wants the instantaneous value, we have to do what? Put it in terms of cosine of omega t minus beta z. But in the answer, does he have that form?
You said instantaneous value.
Just the magnitude?
You said
it's-
instantaneous value. I
yeah,
got a
but it
little,
changes.
yeah.
You gotta understand something. If when you have a time varying waveform, at any instant in time, it has a different value.
So then what we solved for is fine if t equals 0.
Well,
Right.
really, it's the magnitude of the E field. But I think that's not exactly a clear statement of what he's asking. Okay, that's a good question, though. Next. Does everybody follow me on this one? Now we're going to do shields. So I'm going to take this and I'm going to take it a step further. This is in the book in chapter 9, I believe. It's shielding. And this is going to be an arbitrary shield, but I got to show you how to do this. I'll give you the page number in 1 second. Actually, you need to get. Did you find it? This is not my book. It's actually. Let's see.
Would it be under attenuation? Oh, wait, here it is, 9.5.
All right, yeah, it's on page 524, section 9.5. One probably right there. Okay. So with shields, here's what happens. Now I'm going to have something like this. I'm going to have a shield here. And the shield's going to have a thickness, and I'll call it thickness T of the shield. We can call this point Z equals 0. And I'm going to do it this way for shields. I'm going to call this air region 1. This is going to be region 2, and this is really for the shield right here. And it has a thickness T right here. We're going to assume the shield has some sigma shield, some epsilon shield, and some mu shield. And then we're going to have region 3. Now what we're going to do is say this. We have an electromagnetic, we're going to assume that's the Z direction. This is the Z direction. And this is the X direction to keep it consistent with Dr. Wentworth's book. And we're going to say that I have an electric field that is incident in this direction. It's propagating this way. It strikes this shield. Some of it is reflected in this direction. And some of it is transmitted into the shield. And then this is going to keep on propagating and hit, and some of this is going to be reflected. And so forth. Do y'all follow me? What we're after is this. We want to figure out the electric field transmitted. That's what our goal is. And then we'll find a way of actually attaching a figure of merit to that we call the shielding effectiveness. So what is a shield? It's something, you're trying to shield something from electromagnetic radiation. So this is typically made of something like copper. It's very thin. It could be of the order of maybe tens of microns, maybe 100 microns thin. Very small, very thin. And it's around, or it's preventing electromagnetic fields either from getting out of region or from entering a region. And a good example of like a type of shield like this. This is a stainless steel case on here, so this laptop's, it's not very thick, the sheet metal on this, or whatever, I think it's a sheet metal, but it acts as a shield. No electromagnetic wave can really penetrate effectively at a higher frequency at least and get into here and mess with my electronics on that. That's the idea behind this, and I think everybody understands the philosophy. It's basically to prevent things from getting in. And so the air is like the outside, and we want to figure out the transmitted field. So here's what we have to do, and it's just an extension of what we've done. We first start, and we need to get eta in region 1 And we need to get eta in region 3. Here, I assume both of these are just air, so it's eta naught over here, and this is going to be eta naught. Then we have to find eta in the shield. And I might as well put it here. Eta in the shield itself would, of course, be the square root of j omega mu over sigma plus j omega epsilon in the shield. And that's going to have a magnitude of being shield, and it'll be at an angle, probably 45 degrees if it's a decent shield. And then you're going to have to get the propagation constant in the shield, which will be alpha plus j beta, and that's the square root of j omega mu times sigma j omega epsilon in the shield. And I'm trying to make sure you understand these are all constants or all values associated with the shield. You all with me? Everyone? Now we're going to have that. We got 82, and we know that over here, beta is basically beta in region 1 is equal to beta in region 3 is equal to omega over c. And the reason we know that is because the frequency never changes of a waveform as it propagates in a linear material. Frequency will never change. Wavelength will, power density will, a lot of things will change, but frequency never changes frequency. And you know, beta in a lossless region is just what? Omega times square root of mu epsilon. Well, square root of mu naught epsilon naught is 1 over c. That's the reason this holds true. So this is the form. Now, after that, there are a couple of coefficients we have to get. And the first is the transmission coefficient here. So the transmission coefficient here, I'm just going to label this as tau 1. All right? And we're going to need the transmission coefficient here, tau 2. You with me, everyone? Now here's where it gets tricky. If you think about this, I'll try to make it clear. I got a wave coming in. It's going to come in. It's going to hit, right? Some of it is going to be reflected. Some of it's going to be transmitted. It's going to propagate and hit. And then some of that's going to be reflected, come back. So it's going to go bang, 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 and so forth. You all follow me? Do you all remember back in EMAG 1 when you did the bounce diagram? How many remember the bounce diagrams from EMAG 1? One of the things you realized is that this type of a bounce diagram, to get the total amount of voltage that's going to propagate through or into the load of the transmission line, is something where it's really kind of an infinite series approach there, right? Now, if we have a constant frequency with the transmission line, we don't do anything. Remember, these are at a constant frequency. Do you all follow me? The way you did transmission lines at a constant frequency, you did this. You said, if I had, and let me just put this up here, you don't need to write anything down. But you said, if I had a transmission line, and I have a load over here, and I suppose I had a resistor here, RS, and I had plus and minus some Vs. And what I wanted to do was figure out what the V load is right here, but we're at a constant frequency, and there's some characteristic of Z naught. Can you all appreciate the problem? Do you remember doing this? Again, this is not something where it's a transient, this is a steady state operation. Do you all follow me? Constant frequency. Remember how you did it? How many do? You don't have to tell me. Well, the first step you did was find something right here, which we call V prime, and that's the voltage just on the other side of that transmission line connection point. Do you all remember that? And the way you got that was you first had to get something that we turned the input impedance, and we said Zn was equal to Z naught right here, and it was times what? Well, it was times Z load plus J Z naught times the tangent of beta L over Z naught plus J Z L tangent of beta L. If it was lossless, and you found that out, do you remember that? Or if it was lossy, it wouldn't be a can there, it'd be a hyperbolic can, you'd lose the J. That would be Zn. Then what you do is say that V prime here was equal to Vs, right? Whatever that scalar value is, Vs, and it would be times Zn, this value, over Zn plus Rs, and you would get V prime right there. Do you all remember that? How many do? If you can give me a page number, you got the book right there of where this is with transmission lines, please do, and I'll give it to everybody so you can refresh your memory if you don't remember stuff. Now that V prime is very important because there, normally we put the load here at Z equals 0, and we say V prime is comprised of a forward propagating wave. Normally we say V of Z, if it's lossless at least, is equal to V0 plus e to the minus J beta times Z plus V0 minus, and actually the way they did it in your book, if you remember, that was going to be plus the reflection coefficient at the load times e to the plus J V beta Z. And what you ended up doing is saying that you're here, if this is 0, then this point right here would be Z is minus L. So you get V of Z as minus L is V prime, you get V prime is equal to V0 plus times e to the minus J beta Z plus, or I'm sorry, e to the plus J beta L because Z is now minus L plus the reflection coefficient of the load times e to the minus J beta L. And we've got V prime, you could solve for V plus. Does this bring back memories? Now once you had V plus, if you wanted the voltage, well, you can get it by just dividing V prime by this exponential business. Then you could find voltage at the load would be equal to V at Z equals 0, and that's simply equal to V0 plus times 1 plus the reflection coefficient of the load, and you could get it that way. So I'm just trying to make sense of what I'm about to show you. Do you remember this? How many do? What page is it on?
The 31, or transmission line starts on.
Page what?
That's chapter 2 starts on 31.
Now what page is
The
this?
V prime and Zn is on page 55.
Page 55. Okay, everybody? Page 55. This is great. All right, now we're going to use this approach to do this problem. Here's what we do. And he shows us in the book, right? And here's what happens. I'm going to erase this part and I'm going to draw what he draws. He's going to draw the transmission line equivalent of this problem, but I want you to just follow me on this. So he has this. He's going, let me just, I want to see where, in his book, this is in chapter 9, not just these are. In his book, this is on page 527, he does the diagram I'm about to show you. And he keeps it with right at, he doesn't even number this. Right below the figure 9.25, he has the Zn equation, and unfortunately, he doesn't have a number there. But I'm going to try to make sure you see this. So if we think about the transmission line equivalent or similarities between that, here we're going to have air, and then we're going to have the shield, and then we're going to have air, And he's saying what this really looks like is a transmission line right here. The thickness of the transmission line, I think, is it T or D in there? Can you just tell me?
He uses D.
All right, he's saying that this thing has a thickness of D. Over here, now, what I'm going to do is change things appropriately, in my opinion. Before, over here, we had load as ZL. That is the impedance of air over here. Well, that's just going to be eta naught. It would be like the load. Can you all follow me on that? That would be the impedance of air. Over here, you're going to have the characteristic impedance of the shield. Can you all follow me? Right? Then, at this point, instead of having a ZN, now his book, he does use Z, but I'm going to say this point right here, we're going to have an eta N. This is the effective input impedance of the shield, that it has a similarity to what that transmission line input impedance is for a short transmission line. And this is going to be equal to eta of the shield. So the Z naught here has to do with the impedance here. This impedance is actually going to be complex. And then it's going to be equal to eta naught. That is the load impedance that you see the next part. But instead of a J there, because this is lossy, it's going to be plus eta of the shield times the hyperbolic tangent of gamma, which is the propagation constant times thickness of the shield, which is D, over, and this becomes eta of the shield plus, and now it becomes eta naught here times the hyperbolic tangent of gamma D. And that would be the input impedance right here, likened to this input impedance here. Take a moment and just absorb what I've said. I'm using eta instead of Z. He uses Z in his book.
The first term is eta naught, right? So eta S.
Eta
Right.
naught is the load impedance, right? If you take a look here, I'm trying to replicate
Oh, yeah, okay, I got you.
this, all right? Well, eta naught's the first term. That eta naught is really, well, hold on. I mean, that should be eta shield first. Yeah, it is eta shield. This is eta naught next one. Y'all with me on this? Jonathan, can you see it okay over there? Everybody good? And I'm going to tell you, the biggest problem you're going to have with this one is this. But I'm going to show you some tricks. Now, do you have hyperbolic tangent calculations on your calculators? I don't know. The old ones used to. Does yours have that?
Yeah, it does.
Which kind is that?
To inspire.
A TAI Inspire has it? How many have that? Because a lot of calculators, if they're cheap at least, they might not have that. It's not commonly used. You can get it by through exponentials, but I prefer to just write this way. Do you see it? What
Yeah.
kind do you have?
TI-84.
I think it has it.
You gotta go under like,
It should be tan H, I think. Or like hyperbolic tan or something like that. But I really don't know. Anyway, if you follow me on this, now just think of the process. Once now we got everything. And so normally what they want is, first thing they need to do is find out how much that field right there jumps on. And you can think of the characteristic impedance over here as eta naught, like this is eta naught, and here is like your ideal electric field that has a value plus or minus E naught incident. I'm just trying to give you the similarities. You with me, class? Okay, now follow me. I need to calculate this V prime here would occur over here for this thing. So this V prime right here would be equal to, and I won't even use V prime, I should use E prime right there. So E prime, right there, would be equal to, and you know, the transmission coefficient is 2 times the impedance you're going into, which would be eta n over eta n plus eta naught. That would be the transmission coefficient, right? Or better yet, why don't we do it this way? Tell you what, we'll do it this way. I'm going to say that E naught prime would be equal to the incident electric field, E naught incident. Then it's going to be times the input impedance that I'm going into, which is eta n over eta n plus eta naught. And that would be the amount of the field right here. Now in his book, I gotta be a little careful because he's using voltage symbols, not electric field symbols. And he skips some steps, but right here, I don't know the number of this equation, but it doesn't have one. If you go on page 528, go down 1, 2, 3, 4th equation, he's going to show you what I'm about to show you. So this is E prime, and it's right here. Follow me? And it's just like this V prime. Well, what is V prime equal to? It's equal to this, isn't it? So I'm going to say this. My E prime here, I'm going to rewrite it down here, is equal to E naught incident times eta n over eta n plus eta naught. And that will be equal to E0, and this would be E0 on the shield, really, E0 on the shield. So this is going to be the electric field on the shield, and it's going to be times E. Now normally it would be minus gamma times D, but because I'm putting this at 0 here, this is at 0, and this point would be at Z equals minus D, then this is going to be E to the, and here it would be positive gamma times D plus the reflection coefficient below times E to the minus gamma times D. That's E shield is what I need, E0 shield. So I have to divide this by that, and I find out that E0 of the shield is equal to E naught incident times eta n over eta n plus eta naught. And then it's going to be times 1 over E to the gamma D plus reflection coefficient below E to the minus gamma D. And that's the shield, the electric field E0 on the shield. Now we're almost done, but that is shown, you all have your book. He's calling that V0 plus. It's the 4th equation on page 528, if you write it down. You all have access to books? You have a PDF of the book? Or? All right, please make sure you see this. So now what we have to do is this. We have this, and we want actually the value of the electric field that gets out here. Y'all follow me? So what we can do is say it's like the voltage at the load. The E, and it would be, I'll call it E0 transmitted. And that's going to be this value, E0S. And then it's going to be times 1 plus, and here it's going to be the reflection coefficient at the load, which is equal to E0 S. Now the reflection, 1 plus reflection coefficient is transmission coefficient, so it's times transmission coefficient at the load. And here's the nice part, that means it's E naught in the shield, it's that value right there. And what is the transmission coefficient? If you think about it, if you just have this, if you have region 1 and region 2, and what is the transmission coefficient here equal to? Assume that this has eta 1 and this eta 2. It's equal to what? 2 times eta 2 over eta 2 plus eta 1. Isn't that right, class? You all remember that? It's twice the impedance you're going into over the sum of the two. Now, I did it for a reason. If you look here, this is 2 times the impedance you're going into, which is eta naught, over eta naught plus eta shield. Now, typically, eta shield is orders and orders of magnitude less than eta naught. Are you with me, class? And that means that typically, right here, that the electric field that's transmitted is approximately equal to E naught S times 2. Because honestly, if you cover that up, you've got 2 times eta naught over an eta naught is 2. It's usually a value of 2. So if you take this value right here and you multiply it by 2, you're going to have, it should be eta naught right here. You're going to have the actual value that's transmitted into the second region. Can you all follow me, class? I know there's a lot there, but you with me on this? Now, here's the shortcut, which is usually applicable. Not always, but usually. Now I'm going to do it right here. So, if we have a shield, and the shield has a thickness D, and there's some eta of the shield and some gamma of the shield, we've got an incident electric field here propagating in. You want to know what this is. The transmitted electric field. Here's the thing you look for always. You're operating at a given frequency, right? So here's what you look for. You find out what the skin depth is. Skin depth is what? 1 over the square root of pi f mu sigma. It's 1 over alpha, isn't it, class? And if B is greater, really, it doesn't have to be much greater. So say it's 3 times what the skin depth is. So it's at least 3 skin depths thick. Remember, a skin depth, 1 skin depth, you go in, you go down by about 30%. You go in 2 skin depths, now you're down to like 0.1, 0.2%. 3 skin depths, you're basically, it's gone. Here's what happens, is the way it gets in here, if you were to take a look at the magnitude of the electric field that gets into a shield, if this much gets in, it's going to die out. And remember, this wave's propagating in this direction, so the wave, even the reflected wave that's coming back, it's almost nothing in this direction. So you don't have to worry about multiple reflections. Do you all follow me? Everybody? So if this is the case, which it is for any decent shield, where it's not a shield. I mean, there are some super thin ones because they need to make them super light, and they use the multiple reflections because of like they're launching missiles or something. They're launching satellites. If this is the case, and it's just an approximation, then you can say that the electric field transmitted Now follow me. Got an incident field here, right? I'm gonna do a couple things. I can say that my eta in here is just approximately eta shield. You don't need to worry about the transmission line formula for that. Does that make sense to everybody, class? If it's got if it's several skin depths thick, then over here doesn't know what's over here because the information, there's no way it can propagate back. Do y'all follow me for a constant frequency? So if that's the case, I can say this is equal to transmission coefficient right here at the first region, tau 1. Then as it gets in here, I have an electric field that gets in here, and that value that gets in will start decaying at a rate of skin depth. Okay, so I'm going to say the transmitted field would be transmission coefficient times E naught incident, and then it will be times E to the minus skin depth times D. Now it's decaying because this thing's got a total thickness of D, and once it gets in here, it's going to exponentially decay until it hits this boundary, the other side of the shield. Do you all follow me? You follow me or no?
Isn't it like times alpha D?
Oh, I'm sorry. Alpha. What? Sorry. You're absolutely right. I was going to put gamma. It should have been alpha, but you could put a gamma there too. Whitmer's book has gamma, I believe, if you're looking there. I think, right? He uses gamma. It should be alpha. In his book, he'll use gamma, but gamma is just, it has J beta, but beta is just a phase. We don't care about that. We care about magnitude. So it's e to the minus alpha, even clearer here. So it's going to be e to the minus alpha of the shield times d. And then it's times the transmission coefficient here, which is tau 2. Now, I'm going to write down what tau 1 is and tau 2. Okay. First, for tau 1 here, tau 1 is always twice the impedance you're going into. Since this is assumed to be a thick shield with many skin depths, the input impedance is about eta shield, so it's going to be 2 times eta shield over eta shield plus eta naught. And tau 2 is going to be equal to 2 times eta naught over eta naught plus eta shield. I'll get out of your way. Can you follow me so far, class? Take a moment. Then, what you can see is this, and this is true for almost any shield. Eta of the shield right here is much less than eta naught of air. Thanks for hanging with me. You with me? And if that's the case, it means that this, if you look at this, if the shield is much less than eta naught, then this is just 2 times eta shield over eta naught, because eta shield down here is so much less than eta naught. So this is approximately equal to 2 times eta of the shield over eta naught. And what about this one? What? What does that approximate as?
2.
Just 2. That's right. Because eta of the shield is of no consequence. It's usually on the order of less than an ohm. I mean, 1 ohm maybe. Y'all follow me? All right, now if we have that, come back here. When we look at the transmitted electric field's magnitude, that's transmission coefficient, which is 2, approximately 2 times eta of the shield over eta naught. And then it's times e to the minus alpha of the shield times d. Alpha is just the real part of gamma. And then it's times tau 2, which is about 2. So you can say this is about equal to 4 times eta shield over eta naught right here. And it's going to be times e to the minus alpha of the shield times d. And it's gonna be times E incident. Put E incident here, but it should be E incident here. With me? And now we get to one thing that, can you all read this, by the way? It's in your book. Yes, sir.
And so it goes going back, I thought that said Ada skin, but it's Ada shield, down back here. Ada shield. Ada in is
Yeah,
approximately
SA shield, there's no ADA with skin depth. I mean, it's just, ADA is gonna be just the shielding impedance, characteristic impedance. Okay? Now, it's important you follow me on this part. At this point, we've got the transient electric field's magnitude in terms of it's really in terms of the incident field magnitude. If we take a magnitude of it. So what we look at is the shielding effectiveness. Shielding effectiveness. Shielding effectiveness, or SE, and that's really given as 20 times the log of the magnitude of the incident field divided by the magnitude of the transmitted field. So if you take a look at this, if you divide the incident field by the transmitted field, E naught incident goes away, and you get 20 times the log of the magnitude, and take a look at it. It's really going to be inverse everything, so it's going to be eta naught over 4 eta shield, and then you can take that upstairs, so it's E to the eta shield times D, and that would be approximately the shielding effectiveness. Now, Whitmer's book, which I'm about to look at. He has well, he'll have what I have, but he leaves the minus in there. And this is on page 259. And it's for a very specific example, if you take a look. But this will always, what I've got over there will always work. Now, I know it's a mouthful and stuff like this. So what kind of problems will you get? Suppose I give you a transmitted field of a certain value. And, I mean, if I want the E field or H field anywhere in here, it'd be fair at any point. Y'all follow me? Here's the one thing you have to realize. Inside here, if you take a look at the power density inside the shield, it's different than the power density outside the shield. So I've got to do this one thing. Make sure it's so inside the shield, when we take a look at the average power density, it's equal to 1/2 the magnitude of the electric field in the shield that we're at, whatever point you're at, squared over the magnitude of eta shield. And you can call that E naught incident. Then let me do it this way. I'll call it, better make this a little clearer, so you can get confused. So hold on. Let me do it this way. It will be the electric field at whatever point you want squared over the magnitude of eta S. And then there would be a cosine of the angle associated with the shield here, and this would propagate in the AZ direction. It would be watts per meter squared. Now, I'm doing this for a reason this way. I'm going to say, if you know what the magnitude of the electric field is at any point down here, and you wanted to figure out the power flowing, it would be the magnitude of that field squared divided by 2 magnitude of eta s. Remember, eta of the shield is going to be probably an angle of 45 degrees. It's going to have a magnitude in about 45 degrees. But then you can see there's the cosine of this angle, and the cosine of 45 is 1 over square root of 2. Y'all follow me on this? So this becomes a little trickier. I'm going to just star this thing and be careful with this one. But again, for these problems, the best thing to do is take a look at some problems, and you can be given anything. You can be given incident field, transmitted field, H field in the material, E field in the material at any point, and be able to get all the other information if you have an understanding of the shield. You all with me? All right, then, finally, I'll give you problems on this one. All right, now we're going to talk about polarization, but it's not going to be very difficult. So, what do I mean by polarization? That's the first thing. And it really has to do with how the tip of an electromagnetic field, I mean, what type of shape it traces on. I've got to be clear about this so you understand. This is polarization. This has to do with propagating electromagnetic fields. So let me do something here. I'm going to call this X and this Y, and Z is going to be out of the board. And I'm going to talk about what I mean by different types of polarization. So if I have an electric field that's propagating, and it's only in the Y direction, but it's propagating in the Z, just assume the tip of this marker would be like the electric field. Not like this, it'll come down, it'll invert. Basically, you would have a waveform propagating that way that would have only an orientation vertically, or it'd be either up or down in the Y direction. Y'all with me, class? And the magnitude vary depending on time and space. So if you looked at the tip of the electric field at a given point in time, or given point in space, it would trace out this type of a path. You all see that? That is called linear polarization. Linear polarized waves always occur if you have just wire antennas that are straight wire antennas. If you have a wire this way, charge is accelerated up and down that wire. The electric field will always have an orientation along the line of that wire. And as it propagates, remember, if it's propagating in that direction, the electric field would be this way. If it's propagating in that direction, the electric field would be this way. It's always perpendicular to the direction of propagation, but it has a component that is actually going to project onto the axis of the accelerated charge or the current. You all with me in this class? Now that is linear polarization. If you had something where the tip of the electric field is following this, suppose I'm propagating a wave this way, but the electric field actually has something, if you froze space or froze time for an instant, it would look like the tip of the electric field was rotating in a certain direction. You all with me? That's called circular polarization. If this is the y-axis and this is the x, and you have an electric field that's just rotating like this, if you froze, basically if you're at one given position and you allow time to progress, if with just the same magnitude but it rotates, that's called circular polarization. It makes sense. The tip of that field is just cutting out a circle. Does that make sense? Now, how do you, a little more different, and this is why it's so important. If your thumb goes in the, if you take your right hand, take your thumb and put it in the direction of propagation, and put your index finger in your right hand in the direction of the electric field. If it turns in a way that you would open a door with your right hand like this, more or less it's going in what? The clockwise direction as I'm seeing it. Then that electric field is called right-hand circular polarization. Got a right hand, put your thumb in the direction of the propagation. If the electric field is going like that, that's right-hand circular polarization. If you put your left hand, your thumb in the left hand in the direction of propagation, and your index finger actually is a thing that actually maps out the tip of an electric field as time goes by to get into, that's left-hand circular polarization. That should make perfect sense to everybody. There's nothing tricky. Now, why is circular polarization so important? Does anybody know? Why?
I've done a little bit with it, but like for antennas.
But there's one critical thing, especially for radar. Because if I send out a right-hand circular polarized
You know,
wave,
the left hand.
and if I hit a conducting body, like a plane, the reflected electric field will be left-hand circular polarized, or elliptically polarized, depending on the shape of the object. There are very good filters that eliminate left-hand or right-hand polarization. So if I send out a right-hand at a given frequency, and I get back a left, and I know the time delay between when I sent and when I received, I know the position of the object, and I know it's real. It's not an artifact. It's not somebody jamming. That's a very powerful tool. Also with weather radar. You know, weather radar is used all the time. Weather radar will send out types of polarization, but what you have to understand is, this is beyond what we're going to talk about. If you actually have an elliptically polarized, by the way, I didn't get to this, but suppose you have neither left nor right, but elliptical, where now if the trace on the tip of the electric field is an ellipse, that's elliptical polarization. Y'all follow me? Now, elliptical polarization has its place because, see, as raindrops fall, now, I'm going to not pretend to know everything about this, but as raindrops fall in a velocity field, they may be going sideways. Raindrops are teardrops. They're approximately elliptical. They're not quite. And they're conducting usually. So if I have a weather radar and I have an elliptically polarized, it could even be linear polarized, and I look at the orientation I'm transmitting where I get the maximum amount of signal back from a given, say, thunderstorm area, then I know that's probably the orientation of the actual rain. And I can tell if it's falling from left to right or right to left a couple of different ways, because the only thing I have to do is scan this way. And if it maintains the same reflected field properties, if the rain's falling this way and I scan, I'm going to get the same thing back. If it's falling instead of, I'm trying to do this in a way that's going to make sense. If it was falling this way, I would have, and my angle would be skewed this way, but you're going to have to trust me on that one. It gets kind of interesting. Weather radar uses a lot of tricks, but mainly they use Doppler. And why is Doppler so important for weather radar? Does anybody know? You live in the South, you should know. Yeah, hook echoes on tornadoes. Tornadoes, they have a very pronounced Doppler signature, and they get what's called a hook echo. So that if they're looking at this thing at a distance, they see the actual, on these tornadic activities, they see the velocity coming right at them, very high, and there's a very short distance angularly from that point. They got to go in the opposite direction very fast. That's called a hook echo, because, and those things almost always are things that are caught on radar that they could find a tornado by. It's by Doppler radar identifying it. More on that later. I'm going to give you some stuff. For polarization stuff, the easiest thing is you're going to be given time domain waveforms plotted at 3 different points in time. And you can just trace if omega t equals 0, it's here. Omega t equals like 45 degrees, it's here. Omega T equals 90 degrees split, Z equals 0, you know it's going what?
Circular,
Well, it'd be circular. Pardon?
clockwise or counterclockwise.
It would be what? Right hand from in direction of propagation. This would be right hand circular polarization, right? Okay, I'll let you take a look at some problems. I'll give you homework. I gotta go to a dental appointment right now. If you can, listen, if you need to see me, shoot me an email and I'll do it online or something. But I gotta go to a dental appointment 3:30 or 2:30. Yeah, I gotta feel a little better. Everything's 30. Today,